Hi, okay, so this is work done by constant force. It's 12 a.m. right now, so I'm going to try to go over this as quick as possible. So, we typically learn this in simple science classes. I learned this a year and a half ago, that work is just force applied over a distance. And simply put, the equation is W equals FD, which basically just stands for work equals force times distance. Um, but we can extrapolate this further to work equals net force times distance, or work equals summation of forces times distance, and distance is constant here. And I guess the correct term would also be displacement. But remember that work can be done. Although the net change in kinetic energy can be zero, work can still be done. Or if the net displacement is zero, work can still be done. Just the work cancels out, which we'll get to a little bit later using conservative and non-conservative forces. But work equals force times distance times cosine theta. So what does this mean? It's quite simple. Let's say we have a force vector going up like this. We have a box right here, and we're applying a force vector at a angle right here. Then we have to calculate the force vector along here, and to do so, we'll just take the length of this, which we'll say it's f. So f cosine theta times the displacement, which again is just the same formula, but we're just getting the displace or the force along the x-axis. Quite simple. So yeah, that's what the cosine theta thing does. Units of work, pretty easy to derive. So in the SI system, force is always newtons, which newtons would just be mass times acceleration. So it would be ms squared times kg, or it can be kg m squared. But again, remember that we're multiplying it by meters again because that's displacement in the metric system is measured in meters, so it becomes this. Or you can simply write this as Newton m, which is the exact same thing, just a little bit simpler because Newton just represents that. So you don't have to know this, but in the centimeter gram second system, dyne centimeter is ERG. I'm not really sure too much about these ones because we don't really use them here. So work equal force times distance, and that is not a derivative. When you see the dx equation, it kind of looks like the Leibniz notation, dy over dx, but it's not. All it is, actually, I guess it's displacement in the x direction, but not an infinitesimally small change in x. So, anyways, I kind of went on a little bit there. So let's say that we have a box, and it moved upwards 5 meters, and it moved sideways 10 meters, and the force applied is, let's say, 30 degrees at with a force of 10 newtons. Sine 30 is just 1/2, so that means this is going up 5 newtons. So 5 times 5 meters um, will give us the displacement in the y direction, or this fy dy, because it's the force times the displacement in the y direction. And if we do the cosine here is actually a little bit different. Square root 3 over 2. That's because I know my special right triangles. So square root 3 over 2 times 10 simply is 5 square root 3, which is the work in the x direction. Add these two up to get the total work done. And the reason why we measure y and x is because these have no overlap. So let's say we measured y and then a 45-degree angle work in this direction. That means we're overlapping this entire region right here, and we're counting it twice. So unless you can account for that in some spectacular way, you can do so, but I'd rather not, and that makes it a lot more complicated. But we do cover that a little bit when we talk about conservative and non-conservative forces. There's also even further extrapolation. So remember the sigma series notation. That's of F, because that would just be the net force technically, sigma series notation, because we're adding all the vectors of force times displacement, which is the same thing as F net D. So an example of this would be, let's say we have 10 newtons here, and we move a total of 20 meters. And we also have a 2 Newton force pushing right back. And these are not super linear. These are I think it's called bilinear, collinear. I'm not too sure, but they're both pointing along the x-axis. So that means this 10 Newton force would be 10 times 20, which is just 200 um, joules. It would be joules. Because joules is newtons times meters, and then backwards would be 2 times 20, and it'll be negative because this is technically negative. If we consider this as positive force, then this would have to be negative force. That's negative 20 joules, so we did a total of 180 joules, but guess what? We can also just subtract the force vector, giving us a total of 8 newtons times 20, which would just be 160 actually. Oh, sorry, that would be negative 40 and 160. So I did the math wrong, but thank goodness I was able to correct it. One more thing, this is simply just F net times D. So that is your derivation right there. Quite simple, quite easy, 6.1, done.